slope and deflection of frames using Castigliano's second theorem. Basically, we have already understood that in using the Castigliano's second theorem, all we have to do is get the integral of the moment or the internal moment caused by the loads and its partial derivative as the product with respect to p. And of course, we're going to multiply the integral with the 1 over ei. This is due to the internal strain caused by the loads being applied. And of course, instead of adding the summation of SUL over AE, then we are going to neglect this axial since we're not trying to quantify the deformation along its longitudinal axis caused by the force acted on the area, transverse area of the section or of the material. And at the same time, we are not trying to consider this breaking of the material because all we have to quantify is the strain, the elasticity or the elastic member, and we're not going to break it, so therefore we're going to equate that to 0. And leaving that as that equation, deformation, so that the deformation is equal to 1 over ei, the integral of the moment or internal moment times the partial derivative of moment with respect to p dx, and in the direction of the desired deflection. So if the deflection says downward deflection, then you're going to place p at the point where deflection is being asked in a downward or in a vertical sense. And if you'd like to get the horizontal displacement or deformation, then at the point where deflection or deformation is being asked, then therefore you're going to place the horizontal p load there. And so as with the moment. So for slope, all we have to do is get the partial derivative of the internal moment or internal strain with respect to the m prime, where m prime is the load being applied at the point where slope is being asked. And it goes again, it goes the same way in solving for beams. So creating positive bending for a section in frames, for example, we have that kind of frame, then that type of rotation should prevail whenever you consider the lower portion of that member. So it should be counterclockwise. And then whenever you consider the upper portion of that member, then the moment's direction would be clockwise. So also in the middle member, that would be the consideration of the rotation of the moment. If you consider the left side, then it's going to be counterclockwise moment direction. And if you consider the right side of that moment, then of that section, then you will have a clockwise for the moment rotation. And lastly, if you have the right side portion of the frame, the moment direction would be like this. So if you consider the upper portion, then it's going to be counterclockwise, and the lower portion would be a clockwise direction. That's how to create bending moment in sectioning for frames. So we are going to have assumptions made in drawing the elastic curve. Number 1, the distance of the cord joining the ends of the member remains the same before and after the formation, or before and after deforming. Of course, if you have observed that the SUL over AE is being equated to 0 because we wanted to have the axial deformation as not part of the reason of the displacement, but rather we will be only considering the forces or the load being applied to the frame in such manner or in such a way that the points or the distances of the points from every member or for each member would have the same length. For example, if that is 4 meters in the middle before the application of the load, then after the application it would still be the same 4 meters if you try to see that. Also, number 2, the deflections are made perpendicular to the member. For example, that member, vertical member at the fixed support, then if you try to get the deflection or displacement then the deflection would be perpendicular with that member. Since the member is vertical, then the perpendicular of vertical is horizontal, or the transverse. And then for the on the other side, if you try to focus on the upper right side or upper corner of the frame, then we would be able to quantify also another deflection, which is vertical in alignment, right? And also in the same manner with the other point. And if we wanted to get the deflection caused horizontally at the free end, then it's going to be perpendicular with the member vertical on the right side. Okay, number 3. The joints are rigid, such that the angle between the members at the joint remains the same before and after deforming. Of course, in continuation with number 1, that before and after the formation, the length would still be the same. And also, we would always be considering that the supports are rigid. So it's not going to deform, it's not going to twist, or there would be no physical changes. So as you can see, if that portion of our frame would be 90 degrees, then it would still make 90 degrees after the load being applied. Number 4, when a member rotates, the end travels in a straight line perpendicular to the member. So this is somewhat just the same approach that whenever there is an action or there is an action applied at a certain point prior to ending of the frame, then the displacement of a certain point be um, would be in a relation sa final product of the deformation at the end of the frame. So it correlates with the deformation at the end portion of the frame. So in this manner, it's something like that. So kung unsa deformation sa left side, it can cause deformation also, or it could affect rather. It would also affect the deformation on the other side, and so as with the end of the frame. So they are interrelated. Let's proceed to our example.